Hello and welcome. Today we are diving deep into a material that powers, well, literally everything in our modern world. I'm talking about the phone in your hand, the computer on your desk, even the most advanced AI. We're talking about the unsung hero of the digital age, the semiconductor. So let me start with a question for you. What is the one thing that connects your smartphone, a solar panel soaking up the sun, and a powerful microchip? You probably guessed it. The answer is a semiconductor. And look, understanding them is understanding the absolute bedrock of all modern technology.
Okay, so to really get what makes this material so special, we first need to look at how different materials handle electricity. You can kind of think of it as a spectrum of conductivity.
On one end of the spectrum, you've got conductors, right? Think copper wire. Electricity just flows right through it. On the complete opposite end, you have insulators, like rubber, which stop that flow cold. But right there in the middle, and what I like to call the Goldilocks zone, are semiconductors. Now here's the kicker. Their conductivity isn't just in between. The most important word on this slide is controllable. And that control, well, that's everything. This image shows us why that's possible, right down at the atomic level. See, for electricity to flow, tiny particles called electrons have to jump from a lower energy level, the valence band, to a higher one, the conduction band. Now, in an insulator, that gap is huge. It's almost impossible for an electron to make that jump. In a conductor, the bands actually overlap, so electrons move around freely. But look at the semiconductor in the middle. The gap is small enough that just a little nudge of energy lets those electrons leap across. It's just right.
So that brings us right to our core definition. A semiconductor is a material, most famously silicon or germanium, whose ability to conduct electricity isn't fixed. It can be tweaked, managed, and precisely controlled. That ability to be manipulated is its superpower.
But, there's a catch. In its natural, perfectly pure state, what scientists call the intrinsic state, a semiconductor is actually, well, it's not very useful. Let's dig into why that is.
So a pure or intrinsic semiconductor is just a perfect crystal of silicon. The problem is, at room temperature, it has very few electrons that are free to move around and carry a current. It basically acts more like an insulator than anything else. So we've got this material with incredible potential, but in its pure form, that potential is all locked away. So the question is, how do we unlock it?
Well, the answer lies in a process that completely revolutionized this material and, honestly, paved the way for our entire digital world. And that process is called doping.
Doping is the secret sauce. It's the process of intentionally and very precisely adding a tiny amount of an impurity into that pure semiconductor crystal. Now, this isn't contamination. It's a deliberate upgrade. We're talking about adding maybe one impurity atom for every million silicon atoms. It's an incredibly small change, but it fundamentally rewrites the material's electrical properties.
And this slide really shows you that transformation perfectly. On the left, you've got the before, a pure intrinsic material with low conductivity, not much use for anything. But after doping, you get the after on the right, an extrinsic material with high and, more importantly, controllable conductivity. This is the stuff that built our world.
But doping isn't just a one-size-fits-all thing. By choosing different impurities, we can actually create two very distinct and complementary flavors of semiconductor, N-type and P-type. And this is where things get really clever. So first up, we have N-type. The N stands for negative. Here's how it works. We dope the silicon with something like phosphorus, which has 5 electrons in its outer shell. Now, silicon only has 4. So when that phosphorus atom joins the crystal structure, 4 of its electrons form bonds with the silicon, but that 5th one is left over. It becomes a free electron, just roaming around ready to carry a current. You can think of it like adding an extra player to the team. So because we've added all these extra free electrons, they become the main way that current flows. We call them the majority charge carriers. The few empty spots, or holes, that naturally exist are now way outnumbered, so they're the minority carriers. In N-type, it's all about the electrons.
Now for the other flavor, P-type. The P stands for positive. This time, instead of adding an extra electron, we create a shortage. We dope the silicon with something like boron, which only has 3 outer electrons. When it joins the crystal, it creates a vacancy, a hole, where an electron should be. This hole acts like a positive charge. It's like an open parking spot, and it attracts a nearby electron to jump in and fill it, which, of course, leaves an empty spot where that electron used to be.
So, in P-type material, these holes are the majority carriers. The current flows as these holes appear to move through the crystal.
The few free electrons that are floating around are now the minority carriers. It's the perfect mirror image of the N-type.
So now we have these two special materials, one with extra electrons and one with extra holes or empty spots. On their own, they're pretty interesting, but when you put them together, that's when the real magic begins.
Let's do a quick recap. This table lays it out perfectly. It all comes down to what impurity we add. For N-type, we add something with one extra electron. For P-type, we add something that's missing an electron, creating a hole. They're perfect opposites, each engineered for a very specific purpose.
And this is the payoff. This is why we did all that work. When you join a piece of P-type material right up against a piece of N-type material, you create a special boundary called a p-n junction. And that simple junction is, without a doubt, the single most important structure in all of electronics. It is the heart of diodes, transistors, solar cells, you name it.
And this quote just says it all. The entire journey, from understanding pure silicon to the revolution of doping to creating these N-type and P-type materials, it was all about one goal: gaining precise control over the flow of electric current. And we do that by manipulating these electrons and holes. That very principle is the engine behind all modern electronics.
And the impact is just staggering. Look at this. A massive 57% of all semiconductors that are made end up in our computers and smartphones. Just think about that. The device you're probably watching this on right now is powered by the very principles we just walked through. So our entire digital civilization was built on a simple yet absolutely brilliant idea: controlling the flow of tiny particles in a piece of silicon. It really leaves us with one final exciting question to ponder. We figured this out. What comes next?